Hello, and thank you for the opportunity to participate in the Afwerx Space Challenge focused on resiliency, which is aligned with RunSafe's mission. We're about cyber defense. We're about immunizing your software against attack and disrupting hacker economics. And that disruption of hacker economics comes from our senior founders in our development team who come out of the US government attack side, cyber attack side. And when they were involved in crafting cyber kill chains for the US government on the attack side, they would often make use of memory corruption vulnerabilities, exploitation of those memory corruption vulnerabilities up to 75% of the time when crafting their kill chains. And so with RunSafe, they've moved to the defense side, and mitigating those memory corruption vulnerabilities is the disruption to hacker economics. And with our automated tool, Alkemist, that mitigation comes without slowing down your developers. We've seen good implementations with Navy and Air Force. I'll talk about some of those later. And I think applying Alkemist to space assets is another good use case. So memory-based vulnerabilities in compiled code exist. They're exploited. This is a study published by MITRE back in 2019. They published the top 25 vulnerabilities. You'll see the top one is a memory corruption vulnerability, as are numbers 5 and 7. So that's 3 of the top 10. They've given them quantitative scores in terms of importance out of 100, and the top one has a score of 75 out of 100. So these are significant weaknesses. These are exploited weaknesses. They exist in compiled code. And the way a hacker takes advantage of a memory corruption vulnerability, like a buffer overflow, a stack overflow, a heap overflow, is through a ROP attack, remote-oriented programming attack. And this depiction here, this graphic depiction, shows taking legitimate text and making it into a ransom note. And that's the process a hacker of a ROP attack. They're going to take advantage of a memory corruption vulnerability, and then they're going to have access to legitimate code, and then they're going to make it into code used for their purposes, for nefarious purposes. The way you cripple those attacks is deny the attacker the information about the location of those memory corruption vulnerabilities. So in this graphic, the left-hand side is an unprotected piece of software, those memory locations. The middle is that same piece of software with ASLR applied to it, address space layout randomization. That's a process that's been around for a while. It's not really about randomization. It's just an offset from the original memory locations. So a hacker can undo the ASLR offset through an information leak. The third column is RunSafe's Alkemist approach, where the randomization is at a much more granular level. In our work with NavAir, when we were hardening their FADEC, full authority digital engine controller, that produced 2 to the 32nd variations. So high granularity, and denying the attacker information about location denies them the ability to exploit those memory corruption vulnerabilities. So this is a depiction of our tool's automated nature. We're not going to need cyber expertise from your teams. What we need is their software expertise, their mission understanding. They're going to decide what source code, what compiled code to apply Alkemist to. The application, the integration of Alkemist into your existing software and configuration management processes is straightforward. It's going to yield protected code. It's going to yield protected code that has that memory location randomization and denies the attacker the ability to exploit those memory corruption vulnerabilities. In terms of Air Force, we've got a great project underway, actually funded by Afwerx, where we're taking our core product, Alkemist, and extending it in a few ways to better support Air Force DevSecOps CI/CD tool chains, but also better support our general customers as well. We're working with two DevSecOps projects inside this Air Force 76th SWAG Software Engineering Group, one ski camp based in Ogden, Utah, Hill Air Force Base, and one Thunder Camp based in Oklahoma City, Tinker Air Force Base. We also have a project we expect to start by the end of this calendar year, supporting Air Force CROWS program out of Hanscom, Cyber Resilience of Weapon Systems, where, like the project for NavAir, where we hardened a FADEC, this is another critical flight application where we'll use Alkemist to harden the flight management system. And so last slide, just to introduce the demo that Kenton's going to take you through. It's a before and after, showing a vulnerability that can be attacked, then hardening by RunSafe, and then that vulnerability can no longer be exploited.
Thanks, Dave. The demo we're walking through today is on our Alkemist portal, hosted online at alkemist.runsafesecurity.com. To provide some context to the page you're looking at, you can see on the left panel there are a set of instructions and shortcuts. The upper right contains a text editor for editing code, and the lower right contains a live terminal. All of these components are running actively on a server and operating in real time. While the unprotected image builds, let's discuss the components of the exploit's kill chain. Verify password is a simple program written in C that is performing a typical password authentication check. This program contains the buffer overflow vulnerability on the password input. The program dependency, shown here, contains the payload not normally accessed by program operation that gives root control. After an attacker researches the binary, finds a vulnerability, and develops a repeatable exploit, this script is an example of what executes the attack. This script locates the base address of the library in memory and the address of the ROP gadget. Then it fills up and overflows the buffer to redirect the return address to the payload, in this case root access. As you can see, a known stationary recurring memory address is critical for attack success. RunSafe's Alkemist removes the underlying structure needed for exploitation, making it impossible to replicate the attack. Now that you understand the kill chain, let's continue to the next step. This step is just verifying that we have built the image by running a Docker command. And as you can see, it was just recently created, so let's move on. In this step, we will use the discussed kill chain to take control of the unprotected image we just built. The first command is to show program functionality. The password input is super secure, and the output is the RunSafe slogan, 0 days are numbered. Now let's run our Python attack script. As you can see, the script correctly found and logged the base address and the ROP gadget offset to that address, and used that information in the string which overflowed the buffer. By typing in commands such as who am I, you can see that an attacker now has complete control. Let's see what this lethal attack does against a program protected with Alkemist. First, we need to modify the original Docker file and rebuild with Alkemist protections. And there's basically only 3 steps to do this. Let's add the RunSafe image as a stage via the new from line, and let's copy those files into the original build stage. And then finally, let's prepend the Alkemist helper script to the make command and add the cleanup script to remove unnecessary files. This process performs the insertion of Alkemist protections at compile time, making it so the binary is randomized in memory layout every time it loads. Now that all changes to code have been made, we can perform the Docker build command again with the added license key build argument. This last step focuses on proving identical functionality and proving Alkemist protections work against the exploit. Just to refresh, let's rerun the first 2 commands on the original binary. Again, showing the password input super secure and the output 0 days are numbered, and then the exploit, which opens up root control on the container. And the next 2 commands are the exact same, just executed against our Alkemist protected image. First, we verify the functionality remains the same. Running the second command and attempting the Python exploit, you can see that Alkemist has successfully randomized memory layout, immunizing the software and preventing the attack. Due to the attack failing to hit its target, a shell is not open, root access is not attained, and the program stays secure. This concludes the demo, and thanks for watching.